our next topic is on machinery dynamics, rotating machinery dynamics, particularly if you know the dynamics of these rotating machineries, as in general, then probably we understand better the what we call its dynamics, the behaviors, it's the machine's behaviors during operations, or what we call the dynamics behavior during operations. Then from there, uh, itself, we know when these particular rotating machines will have high vibrations or have low vibration, and if it's a high vibration, how it will vibrate or how it will be behave, okay, as a whole of that particular machines. So, uh, uh, in this particular parts or particular sections on machinery dynamics, we will want to know some information on what we call dynamics plus the fundamentals of what we call these structural vibrations. Then from there, we want to relate these machinery dynamics to what we have discussed earlier on quality auditings. Our CBM with quality auditings. CBM plus these dynamic design verifications. If you still remember DDVs, there is a quality auditings. So to make that particular CBM programs better, more to enhance that particular existing CBM programs. So first, we have to know or understand the dynamics of machinery dynamics. So I need to recap what you have learned probably in mechanical vibrations to start out with this machinery dynamics. So you need to know that what you have learned in what we call mechanical vibrations, then we recap back a little bit on this. So in mechanical vibrations or vibrations courses that you have learned earlier, either in your undergraduates earlier, then we treated a complex system or any systems here into what we call a discrete so-called system with represented by a lump mass systems, as you can see here. So a discrete systems, then you have a complex or a real system is a continuous system. So now we treated it as a discrete, okay, what we call finite degree of freedom systems. So here it could be represented as n degree of freedom n degree of freedom systems of any complex or any real system or continuous systems. Right. So when we consider this or we models that particular system in n degree of freedom systems, so this particular modeling itself, if you solve it, then you will have it will lead to n natural frequency and n mode shapes. So natural frequency, if you single degree of freedom, earlier we learned together a single degree of freedoms, you have 1 degree of freedoms, right? You have 1 natural frequency omega naught. But then if you have 2 degree of freedom, you have 2 natural frequencies. Then 3 degree of freedom, you have 3 so-called 3 natural frequencies. Then n degree of freedom, you have n natural frequency. Each natural frequencies will come with its corresponding motions or mode shapes. In this case, we call it mode shapes. At a certain natural frequencies, it will behave at its own so-called mode shapes or motions, model shapes in this case. So if you have n natural frequency, then you have n mode shapes in n degree of freedom systems. Right. So if you take these so-called beams, if you treat it as a 1 degree of freedoms with 1 mass itself, then you have 1 natural frequency, and one here is mode shapes. That's how it moves. The only motion, vertical motion that this particular mass can go is going up, back and forth, but up, down like this, right? Going up, down like this, right? So next, if you have treated this particular beam is as a 2 degree of freedom systems, then you have two natural frequencies, omega 1, omega 2. You come with two mode shapes. So each natural frequency have its own corresponding mode shape. In this case, the first natural frequency, you will see that both mass are moving at the same directions. The second mode shapes, or at the second natural frequency, mass 1 going into down, then mass 2 going opposite directions, going ups, right? Then if you have 3 degree of freedom, 3 natural frequency, then you have a 3 mode shapes. This mode shape, it will basically corresponds to these natural frequencies, and they are what we call these things, not repeated. So you see that the first natural frequency will have all going down, the second natural frequency will this down, up, the middle, ups, then the third natural frequency is down, up, down, it's something like this, okay? So it's always, if this is going up, this is coming down. When this is coming down, then this M1 is going up, M3 is going up. And this motion is what we call a dynamic motions, or what we call vibrations. In this case, is if you represent it, it's a sinusoidal. So basically, it's going back and forth. Right. So if you have a 4 degree of freedoms, then you have 4 masses. Then you have 4 natural frequencies. Then you have 4 mode shapes. Okay, each mode shapes correspond to one each owns natural frequencies. All right. So if you have more than that, then you could have more. Okay. Of course, we are saying that if this particular beam itself, beams are actuals is a continuous system. Okay, so a continuous system will have infinite numbers of natural frequencies and infinite numbers of mode shapes. But then the first 4 natural frequency and mode shape will be the same like what you have seen here, some sort like this. So, but it will have very infinite numbers of natural frequencies. So here we are saying that natural frequency has its own deflection shapes, or what we call the mode shapes in this case. Then continuous systems, I mean continuous beams like this, so you have an infinite number of natural frequencies and its corresponding mode shapes. So when study, so if you want to get as close as continuous systems where you are having an infinite number of natural frequencies and mode shapes, then you need as high as possible number of degree of freedoms. Okay, of course, although it's a finite, so if you have a higher degree of freedom, then you can disclose or extract out the more number of natural frequencies and its corresponding mode shapes. So higher degree of freedoms, you will go more. You can get more natural frequency, and you hopefully can go as closer to the actual continuous systems. All right, so a continuous system or actual system will have infinite numbers, natural frequency, and a corresponding mode shapes. Here we are saying that. Then if you have a steady state excitation frequencies coincide or hit at any of these natural frequencies, resonance occurs, right? You remember that when we say resonance, when the resonance happens, then it will be, we are saying that when your excitation frequencies coincide with natural frequency. So that is in 1 degree of freedom, because you only have 1 natural frequency. But in a n degree of freedom of actual continuous system, you have infinite numbers of natural frequencies. So you have infinite times of possibilities to get into natural resonance conditions, meaning to that you have infinite number of natural frequencies, you have infinite possibilities of excitation frequency coincide with natural frequencies. So that if you have resonance, you know that when resonance, what will happen? Your vibrations or amplitudes will be amplified in our first few topics. We have already mentioned under vibration and resonance. So it will be amplified. So even with a very small force, it will be, because of the resistance is very, very low. So you will basically, low resistance will basically giving you a high vibrations. So this high vibration in this case is not due to high force, but it's due to low resistance. High force is similar like unbalance that you see, misalignments that you see, observe. So this is not purely in this case, a additional or in amplification of vibration is purely due to low resistance. So in the case of you have imbalance, you have a high force, then and it coincide with the natural frequency, high force plus low resistance, then your vibration will be even higher in this case. So n degree of freedoms, right? You have n natural frequencies, then you have n times of getting or experiencing the resonance conditions, right? So that is what it means. So you have to take notes. And if we know when to get the natural, if we know the natural frequencies, where is the natural frequency, omega 1, omega 2, until omega n, then we know when this particular system that we are analyzing, I mean, it could be in rotating machineries, will fall into a resonance. And if we can avoid, okay, we can run it at a frequencies that it have a good, sufficiently good, what we call resistance, then you will avoid resonance conditions. All right. So here, I mean, we are saying that's a dynamic response, or what we call your vibrations, okay, of a systems, the entire motions of the systems, entire motion of the system or the machineries, basically how it vibrates, it basically contributed by the combination of all the modes of vibrations. By theories, you can see that the X, the vibration itself, is actually contributed by the vibrations from mode 1, where your phi is mode 1, mode shape vectors are 1. Mode 1 contributed by mode 2, contributed by mode 3, contributed by mode 4. Right, so if you have n degree of freedoms, right, or your system is in actual is contribute what we call is infinite numbers of natural frequencies. So you have a contribution from infinite numbers of what we call modes or onto your vibrations, and depends which one is nearer to the, which mode is nearer to the excitation frequencies or the running frequencies, then it will contribute more. Those that are further away, okay, from its excitation frequencies, the mode shapes will contribute less in this case. But in theories, we are saying that vibration that you obtain from a machineries, it is contributed by the mode shapes. Right. So the modes that dominates the motions depend on the following factors. So there are 3 factors that affecting these motions. I mean, we are saying that it contributes by the modes, but it will have, we have 3 factors, and when this particular mode is probably, when we say this particular mode is, it can contribute more, then you probably can explain why it will contribute more, why not mode 3, why not mode 1. So there are 3 factors actually affecting these contributions. So the first one is closeness of the natural frequency to the excitation frequencies. Okay, so this is the theories behind if you are looking into a discrete or multiple degree of freedom equations, then probably you can derive out this. I mean, that you have learned in mechanical vibration and degree of freedoms or multiple degree of freedoms. But if you are looking into this itself, or this equation itself, this particular part is this numerator, denominator, under denominator parts, you have this omega, which is your excitation frequency, omega naught is your natural frequencies. So if they is closer, so this particular part is almost zero. So you have a very low resistance or denominators. So you will have a very high contributions of vibration from that particular mode itself. So here, how we see it. So if you have your excitation frequencies omega very close to your omega 2 in this case, or here we can say that it is resonant conditions, right? But in this case, your vibrations, I mean, if the excitation frequency is close to the second natural frequencies, here we are saying that your x, I mean, just now we are saying that your x is your vibrations that is contribute by all the modes, right? But in this that particular examples, so this will be dominance, so the rest probably will not that dominates compared to this particular mode 2 contributions. So in this case, if it happened to be like that, then so if the excitation frequency is close to the second natural frequency, contributions to the response mainly from the second modes. So you can see that your vibrations that you obtain from that particular system, or in this case is the beam itself, you will see that it vibrates like this, which is contribute mainly by the mode 2s. Mode 2 just now. Yeah. Probably you can have a look. So just now we are saying that this is the modes now, right? The mode 1 will go like this, mode 2 will go like this, mode 3 will go like this, mode 4 will go like this, right? But then in the case of when your excitation frequency very close to mode 2 will contribute the most. Then you will see that in your vibrations response of that particular beams, you will see it vibrates some sort like this, your beams, okay? That it's a dominance. This is still there, but then is compared to this, probably in terms of percentage. Just now we show that is less, is 90%, probably 90% is this, 5%, 5%, maybe another one is just this 5, 3, and 2%, right? So in terms of contributions, mode 2 will be larger. So this is when you have resonance happens, so why you will see that the vibrations of that particular systems under resonance, it will vibrate similar like that particular modes that it coincide with. That is because the contributions is the most, the mode is the most dominant in the entire what we call the dynamic response or the vibrations. Right, so that is one of the factors. The second factor is amount of dampings of that particular resonance modes. So is these particular parts. If you are looking into this X itself, is this particular parts. If it happened that that particular modes, you have a damping, this sigma is larger. So you will have, if you have a larger dampings, so your natural frequency peaks will be a broader peaks instead of a sharp peak like this. So if you have larger peaks, you see that your X here, even it is running at a resonance. So compared to no damping or low damping compared to high dampings, so you see that reductions of vibrations reduce. So in this particular case, if mode 2 have a high dampings, then it will reduce the contribution of the second mode to the total response. So your total response probably just now from 70, if that particular mode itself is high enough, high damping enough, then probably from 90, it will reduce to 70% of contributions. Then this mode 3 and mode 1 will contribute more in this case. Then you will see that vibration motions, you have a mix of motions between maybe 1, 2, and 3 in this case. All right, so that is another factors. So here you see that vibrations. I mean, here we are not talking about the force itself yet. It's talking about the resistant parts. So if your vibration, if you want to know why your machines vibrate like this, why your machines vibrate like that, then probably here we are saying that you need to know its dynamics of that particular machines. So here is referring to its natural frequency, damping, and its mode shapes. Then from there, you know that at this particular case, okay, it is resonant case. Your excitation frequency coincide with my second natural frequency. That's why you have higher vibrations. You can explain why it is high and how it vibrates, and it vibrates similar like your mode 2. Right? So at sometimes you have a resonance, but you have a very low vibrations. Okay, you found out that your natural frequency is at, let's say, 20 hertz. You are running your machine at 20 hertz. By right, you have resonance, low resistance, then you will have high vibration. But then you found that your vibration of that particular machine is low, right? So how to explain it? So probably you can look into the 20 hertz, that is the natural frequency, what is its damping values. So probably in that particular case, the damping value is very much higher, right, that it can use to absorb most of the vibrations. So in that particular case, you have its contributions of the vibration from that particular mode is lesser, then your vibration is relatively lower, even at resonant conditions. So that help you to explain also when why suddenly sometimes you have resonance, but you still have a low vibrations. The next factor is interaction between your force excitation, where your force excites, and also the mode shapes. All right. So in the case of, let's say, I mean, talking about just probably uni directions, or what we call a nodal force at one point. So if I have a force at a nodal force at one point, when it act at the middles at here, right? At this particular point, at this particular point in the middles here, right? In the middle of the beam itself. So if the excitation force act at the centers, it will not excite mode 2 and mode 4 as at all, as they are not at this particular positions. So what I mean here, if you have a force at the middles in the centers here, so the motions of the vibration signal that you have, you act at this particular point, it will not excite the modes contributions. Your vibrations will have no contribution from this mode 2 as well as mode 4, because the force, the location of the force that you act at this particular point for mode 2, you see no movement. If you look at my mouse cursors, I mean here, at this particular point, this the one that I'm pointing to is not moving at all. Right? Same with the mode 4. If I point at here, so this point is also not moving. So this particular point with no motions, we are saying that this is the nodes or nodal points of that particular mode. So here, the nodal point of this modes, mode 1 is at here with no motions, or here no motions. So mode 2 is here in the middle as well as in the right, on the right hand side. So that those particular point, when you have a force acting at this particular point, you won't have contribution or in your vibration from that particular mode. So in this case, probably you'll find out that your total vibrations in this case, if you're force acting at the middle, you won't have a contribution from mode 2 and contribution from mode 4. So going back to if you are looking into just now the previous case, so if I have my force is nodal force, but is excitation with excitation frequencies at near to omega 2. So if I acting at here, my force, nodal force with excitation frequencies, this excitation frequency with the steady state frequencies or excitation frequencies of omega 2, which is near to omega 2. By right, you have resonance, but in that case, because the place that you place your force is near to is at the nodal point of the mode 2. Even it is exactly the same, your omega naught 1 and omega naught 2 in omega naught 2 and omega is same, cancel out. Even you have no dampings, you won't have resonance. You have resonant case, but you won't have high vibration because you don't have a contribution from the mode 2 in this case. So contribution from mode 2 is 0. So in this case, even you have a very high, what we call, you have a resonance case running very close to mode 2s, omega 2s, you won't have a high vibration in this case. All right. So another types of these particular factors are interaction between the distribution of excitation force and the mode shapes. Basically, it look into how your force interact with your mode shapes. So in the case of these particular beams itself, let's say you have a first mode some sort like this, second mode some sort like this, or first mode some sort like this, second mode some sort like this. So if your force distributions is same, in this case, your force distributions, okay, you have a what we call distributed force, not a nodal force or concentrated force, distributed force with a frequencies very close to this particular what we call modes itself, then it won't cause any resonance or amplification of these particular modes, but because the distribution of this the force distributions is very close to this, but is similar to this particular modes. So you have 100% or contribution from these particular modes, and this particular mode basically will end up to 0 contributions in this case. So in the case of you have n degree of freedom, n modes, and these force distributions is similar to one of the modes. So you only have the contribution in your vibration or from that particular mode. The rest will be 0. All right. So another one is some sort like this. Okay. So if you have a force in a certain directions, you will not excite modes perpendicular to it. So if you have a horizontals and vertical modes, just now our beams are all in verticals. So if you have if your force acting on verticals, you won't have you only have your what we call your vibrations contribute in vertical directions. So you won't have rarely will have horizontal motions vibration in this particular case. All right, so that is one of it. So perpendicular to it, your modes that are perpendicular to your force itself. I mean, you won't be excited in this case. All right, and finally is symmetrical and symmetrical. Just now you see that we have a distribution that the same, okay, the force distribution that's same with the modes, you have the contribution of the modes. But then if your force is uniformly distributed, as you see here, so in this particular case, if you have anti-symmetrical modes like this, it won't be because when this uniformly distributed act on anti-symmetrical types of mode shapes, then it will be cancelled out. Positive and negative will be cancelled out. So at the end, you will have 0 contributions. Whereas this one is a what we call symmetrical types of mode shapes, then you do not basically so-called cancel out each other. So then you have a contribution. If you have two modes only, like 2 degree two modes itself, then this particular mode will have 100% contribution. Right. So here we want to say that I mean your vibrations I mean itself I mean we don't talk about the force, how high is the force. I mean, assuming the force is very small itself, I mean, then when it is close, okay, when it is close to your natural frequencies, I mean that particular excitation frequencies is close to your natural frequencies, then you have a low resistance, high vibration or resonant conditions. But at some point, at some case, when your particular natural frequencies, the particular natural mode itself have a very high damping, then that damping itself can help to absorb the vibrations. So probably even at resonance case, you have a low vibrations. So at some points, I mean, even I mean, and if your force distributions and the mode shape itself, you have a relations, then you will excite that mode. If you have no relations, then it won't basically excite that mode out. And or in the case of for example, and the one that I have mentioned to you, if that particular force itself acting on the centers of the beam itself, and you have no relation with the mode 2 and mode 4, so even your excitation frequency is close to the natural frequencies, your vibration is still low. In this case, even resonance, you will have a low vibrations. So sometimes people, when you say you will see excitation frequency coincide with natural frequency and you have low vibrations. So that is where these three factors come into play, and these three factors can use to explain why even at resonance is low vibrations. Right? So these three factors can basically, or these three points can help us to explain, okay, most of the vibrations issues, as particularly on machinery dynamics. So when you said the machine's vibrations is high, and why is high, you want to explain, then probably you can come back to these three factors. Right, but to explain further why, I mean, to know which one it is related to, so then beside, for example, in this case, you need to know its natural frequencies, right? The amount of dampings as well as the mode shape factors, right? Mode shape vectors. So you see, I mean, if you want, I want to make use of these three factors to explain any vibrations phenomena, particularly on machinery dynamics. Then I can use these three factors, but then to use these three factors, first I need to know the natural frequency of the system or the machines, right? The damping that corresponding to each natural frequency, and the mode shapes that corresponding to each natural frequency. With all these three informations, then only I can explain, okay, like what I have explained, or I have demonstrated to you. So why it is high, because it's close to natural frequencies. Because if you have one set of where is the natural frequencies, then you know when the resonance will happen. All right. So, and you can find out if you have a set of natural frequency with the damping itself, then you know at a certain natural frequencies that even your coincide with your excitation frequency coincide with your that particular natural frequency, you will have low vibration because you have high dampings, right? And together with the information of the mode shape itself, then probably you will know if you have a force acting on the nodal point of that particular mode, even is excitation frequencies, then it won't cause any high vibration issues in this case. So that three factors basically help us to explain. To know these three factors, you need to know that three parameters are that related to a machinery dynamics, dynamics behaviors. So that is what we call here natural frequencies, the modal damping or dampings, and the mode shapes, all basically corresponding to each of these particular peaks. All right. So if you are looking into these input and output relationships, when you have excitation ins, then onto a system itself, then you have this output outs. So in, out, then this is your system. So if in this case, we are saying that if you know this particular system, then you understand how this system behave dynamically, then from here you can, given inputs, you can explain why your response, you can predict your response or even explain why your response behave like that, or why your system behave like that with a certain response. So you see how important it is to determine this so-called system dynamics informations. All right, so the response of the system is interaction between the dynamic characteristics, okay, or your transfer functions and the excitation or your input of the systems. So you have in, transfer function, and out. So if you know the transfer functions, or what we call the dynamics characteristics here, in vibration we call it the frequency response functions. Then you know the frequency response functions, you know these dynamics characteristics in terms of if the natural frequency, damping, and mode shapes. You know how when vibration will be high, vibration will be low, and how it happens. You basically can explain based on the three factors. Right, so to know this particular system informations. Right, so in most cases, analysis of dynamic system only involve a measurement of response and directly related to excitation. So a lot of time you only measure this, right? So and you if you can get this, then probably you can relate it to these excitations. So you can predict back the excitations. So if you have you want to know this, you have to give a known inputs and the known outputs due to these inputs, then you will have this information. So all basically all of these are actually based on these in-out input-output relationships. All right. So if I want to know this machinery dynamics, I mean, or the dynamics of the dynamic behavior of the machines, then I need to determine this system, or what we call the dynamic characteristics. So to determine these dynamic characteristics, so that is one of the techniques, or what we call experimental techniques that we can use to determine these dynamic characteristics. So here is what we call experimental model analysis, EMA. Right. So this is what we will be later on conducting in the laboratory sessions, performing this experimental model analysis. So if you can perform, you know how to perform model analysis or experimental model analysis, EMAs. So basically you know this, right? In terms of its what we call in terms of its natural frequency, damping, and mode shapes. Okay, so this the outcome of this EMA will give you natural frequency, damping, and mode shapes. So with this information, we will know the system whether it is when it's running, whether it is closeness to that natural frequency, whether it's high vibration because very low damping, whether you have no vibration because your force distribution have no relationship with your mode shapes. So you can explain, okay, different behavior of your machineries. I mean, through these three factors, by knowing these dynamic characteristics, natural frequency, damping, and mode shapes. All right. So that is one of the techniques that experimental technique that we will be learning. On top of this, I mean, we will also want to know the response. Okay, the response is the vibrations. I mean, the vibration. The excitation is the inputs. Okay, the force, right? So if you know this, right? So there is no issue that you can predict these excitations. Or a lot of times, you cannot measure the force. I mean, the force that how to say it, your measurements of the force on your systems, running system or in service machines, you do not know how much force actually created at that particular point, at this particular point. So what we need to do is we measure the response of that particular point, which is vibrations. I mean, you're using what you have learned earlier, the sensors that you are learning, you are measuring the vibrations. Then together with EMA, you have these system characteristics, then you can predict the force. So to know the response itself, I mean, of course, we use vibrations measurements, right? the vibration measurements basically to get you the response. So to study the determine the response of the whole structure, when we say the whole structures, not only one point at the bearings, housings, or 4 point at the bearing, housing of the machines. But here we are referring to, if I want to know how this particular entire machines is vibrating or is moving, is deflecting during operations, then we know the response of the systems. Okay, then that is a techniques, experimental technique called operating deflection shapes analysis techniques, ODS, where you can use to determine the overall movements or overall response of the machines under operations or during operations. All right. So with these two informations, right, you know, okay, how high with this ODS, you know exactly how high your vibration is over the entire machines, not only at that 4 bearing points that you learn in CBMs. In this case, is the entire machines, right? The entire machine, where is the highest vibration point? Maybe it's not fall into that 4. It's not at the 4 measurements, the bearing housing measurement point that we learned in CBMs. All right. But you only know how high the intensity, the severities, right? And what frequencies during excitation frequency, right? But then you do not know the reason why. When you want to explain why, right, then you need that 3 factors, right? These 3 factors to explain why it's high, why it's low, right? Or why at this particular frequency no vibrations. So you need to know its natural frequency, damping, and mode shape. So to know the response, you use overall response. You use ODS to explain why this to explain on this overall response, right? Overall vibrations. You use EMA or experimental analysis, where you obtain the natural frequency, damping, and mode shapes. So here we will be learning 2 types of analysis. So these 2 types of analysis basically can help us to explain the dynamics of the machines under operations. Right. So these 2 will support these 2 techniques. Will also support what we have mentioned or introduced to you earlier. This dynamic design verification, DDVs. When you have your CVM come with this DDV itself, so that basically will further enhance, okay, our that particular maintenance programs. Right. So that is what we have quality auditing. Okay. So the whole idea of this quality auditing basically you includes under the existing CBM, includes this DDV ins, right? So why we want to do that? Okay, the whole idea of this quality auditing is to ensure that, okay, the whole idea is to ensure that your machines is what we call dynamically well designed, meaning to that you have no low resistance issues when it is running at its operating speeds or running frequencies. So that is what we would want to ensure before it actually start in operations. Right? We want to ensure that all the machines, individual machines, are basically having a good dynamic design. Here, the dynamic design meaning a good what we call design when this particular machine is running at its operating frequencies or running frequencies. All right. So why we are saying so, right? We are saying that individual machines usually, usually if you have a component itself, like a motor manufacturer, when it designs that motor, it will perform this dynamic analysis, no issue. You will ensure that this motor have no dynamic design issue, meaning no low resistance issue or no it won't fall into resonant case. Meaning if your motor is running at 50 hertz, the designers of what we call the manufacturer of the motor will ensure that the motor will not have a natural frequency at 50 hertz. Okay, so that is clear. Okay, but then when this machine, your motor itself, you won't do anything, right? You have to combine, you have to assemble with your your drivens, the driver have to assemble with this driven then to do works, right? So however, when these machines are assembled together, the dynamic characteristics of that particular machines will change. Okay, it will change. All right, so that basically the changes probably will fall into low resistance issues or what we call the resonance issues. So without knowing the new assembles machines dynamic characteristics, then you do not know whether these particular assembled machines will have any dynamic design issues or not. So that is the purpose of quality auditing. Okay, with this TDV, we want to ensure that every rotating machineries, when it's assembles and it sit on their own what we call test, what we call the skid itself or the support itself, they are having good dynamic designs. Here is referring to the resistance of that particular rotating machines is good. No low resistance issues, no resonance issue. Right? So if you are looking into this, for example, on individual machine itself, when it is designed, okay, at 50 hertz, right, you will ensure that the natural frequency is all away, okay, from this 50 hertz. So no low resistance issues, no resonance issues. Right, but then when you assemble this motor, for example, this is the motor natural frequencies. But then when it assembles to pumps, okay, sitting on a skid itself, then sitting on the support and a main skid itself, then probably that particular natural frequency will be shifted. Okay, if you've not properly designed dynamic, you didn't really look into its dynamic designs, so you will see that this peak itself now have shifted on using, on this yellow line itself, from this red line, now it have shifted to these yellow lines. And in this particular case, your running frequency is still the same, okay, but then your natural frequency now is very close to your excitation frequency or operating frequencies. Then probably you have these low resistance issues. Right, so if you can know this very in the early stage, during a commissioning, before commissioning or during commissioning, before it start in operations, so probably you can eliminate this, right? That is what the quality auditing works. All right. So here we are saying that if you can eliminate this itself, right, then your CBM becomes your what we call your CBMs, probably just taking care of the machines components that cause due to wear and tear. When basically your CBM will become more accurate in this case, because your procedure of CBM is mainly assuming that, okay, like for example, your imbalance misalignments that was due to the wear and tears of your machine component, your couplings, your bearings, your so-called impellers or whatever that is rotating, that is not, for example, is over 24/7 runnings non-stop, then probably over time, if you have caused wear and tear to these machinery components, then it will create a very high force, in this case, on that particular machine, giving high vibrations. Right? But then if your machines in the first place, you already come with this what we call dynamic design faults, where you have these right, in the first place, is already having so-called low resistance issues, then probably it will cause to misjudge or misanalyze on what you think the machine is actually giving you. The vibration, the high vibration, one time probably you will lead it, you will go into you will say that it's unbalanced, then you go and balance it, try to reduce, but then over time it will go back come again, because the actual root cause in this case is what we call the inherent assembly design flaws or dynamic design faults that are actually causing the high vibrations. So if you can eliminate these inherent design faults, right, at the first place, then your CBM work or job become easier. Okay, so basically, mainly you are looking into or predicting when the machine will degenerate due to wear and tear. Right, so that is the whole idea. Right, eliminating any design flaws. Okay, then it will reduce the condition monitoring tasks. Okay, so you are just looking into the vibration going high is you can actually pinpoint that it is due to this so-called wear and tear or degenerations. Right, so that's where we have these quality auditings, where we come up with this DDV dynamic design verifications. All right, so into this incorporate into these CBMs. So it's to enhance or further enhance the maintenance schemes. First, eliminating the design flaws, dynamic design issues in the machines, right? So this is what we call dynamic design verifications flow charts, right? So DDV flow charts. Okay, what is DDV flow charts? I mean, so if you are looking into this, so the whole idea of these DVs, I mean, it basically combines, okay, your experimental techniques as well as what we call computational mechanics with the hopes, okay, with the aims to eliminate the design flaws or design faults or dynamic design issues of your assembled machines, right? So what you need to do first, of course, similar like I mean, the whole idea is to when it starts in commissions, I mean, before handovers, before it start in operations. So probably you have to go through a round of preliminary analysis. So preliminary analysis is like your CBMs. So the 4 points at 4 point, which is at the driver-driven NDE, DE, DE, and DEs. So you go through all the new machines, okay, just commissions, not yet in operations. So by right, everything is new, okay, right? Everything should be well balanced, right? No wear and tears, and it should give a very good vibrations levels, right? Because everything is new, right? So you can perform your time domain analysis, frequency domain analysis, or even visual inspections, then compare with the standards. If all are goods below the allowable limits, then in zone A, should be zone A because it's new commissions machines, right? If it's in zone B, so it's still acceptable, but then if it's zone C, then probably you have to come to DDVs, right? So if it's zone A, zone B, or new commission machines, but then by right it should be it's good to go. Then if it's acceptable, then yeah. So meaning to that, these machines are all new, have no vibration issues, meaning we can say that you have no dynamic design issues. But those that exceeded or in zone exceeded the allowable limits or in zone C or D, these new machines, newly commissioned machine in zone C and D. So basically, it should indicate something is wrong with that particular machines, right? So to do that, probably you have to perform these DDVs. Okay, to further look into its machinery dynamics, so and see what is actually causing these high vibrations that cause it this newly commissioned machine at zone C and zone D. Right, so that is where you perform DDVs. So DDV basically combine two techniques, compute measurements or experimental techniques, as well as computational mechanical techniques. So experimental techniques basically it combines, okay, what we have discussed earlier just now, the modernization techniques where you learn or you know the dynamics characteristics or dynamics behavior of that particular machine in terms of its natural frequencies, dampings, and the mode shifts. right? Then at the same time, you have this operating deflection shapes analysis where you get the response. The response is not only that 4 points, it's a detailed response, which is the entire machine's motions, right? Entire machine motions, right? During operations. Why it is basically we are looking into where is the highest vibration points and 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 what is this spectrums, how is the spectrum of the overall machines look like, okay, and that basically give us the severities, okay, of the vibrations of that particular machines as well as its motions of that particular machine during operations. Right, model analysis will give us the set of natural frequency damping and mode shapes telling us its dynamic behavior or dynamic characteristics of that particular machines. It will help us to explain why it is vibrating in that particular way or particular motions and why you have a high vibrations. Okay, so that these two can help us to basically explains okay the dynamics of that particular machines. So DDVs is against it combined with computational mechanics. So you will have so-called finite elements analysis coming into place. Okay, so this finite element analysis basically is types of analysis where you build a models. Okay, you build a models that is similar to the actuals. So actual machines, let's say motor pumps sit on the skid. So you build a model that similarly, you have a motor pump sitting on main skids and exactly the same. So to know how close are they or why, how these CAD modelings that you model is exactly the same with the actuals. So of course, usually you have to follow the mechanical drawing when you model it. But then to further ensures, okay, it is similar, your model is similar with the actuals, then you have to validate your models. So how to validate that particular models? By correlate it with the actuals. So through model analysis, right? Model analysis tell us the dynamics, behaviors or dynamic characteristics of that particular machines, right? So the model itself, if you perform finite elements, what we call model analysis, that is a tools or the features where your model itself under finite element analysis, you can perform computational model analysis where you will give you a set of natural frequency and mode shapes. So this a set of natural frequency or mode shape is of your this particular CAD model itself. By right, it should behave the same with the actuals. So if you have a same set of natural frequency and mode shapes, okay, in this computational model analysis with the experimental model analysis, then meaning to say that your CAD model is behaving the same dynamically with your actual systems, actual machines. Then we can say that the CAD model is validated. Right, so one is validated, right? Then we can know what is actually the issues of the machines. Okay, why it's high. Okay, through this ODS model itself, model analysis and ODS itself, operating differential analysis itself, then probably we know, yeah, because it is high because you have a low resistance issue or resonance issue. So you can identify that particular problems, right? So if you can identify this particular problem, which is a resonance issues or dynamic design issues, then you have to improve this so-called dynamic designs by changing what we call uh, the set of the natural frequencies that close to your excitation frequencies, right? So because your excitation frequency is close to your natural frequency in that case, right? So if you can shift your natural frequency away, then you can have low resistance issues being rectified or resonant issue being rectified. So how to shift it? By modifying the what we call the machines, okay, by modifying the machine that is under resonance or you have these dynamic design issues. So We don't modifying on the actual models or actual machines. Okay, we modified on the CAD models. So this CAD model earlier have been validated. Okay, basically this model is behaving the same with the actual models, right? So these actual models, basically CAD model is behaving the same with actual model, meaning whatever that I changed on this actual model, CAD models, okay, it will behave. The actual model behave the same also if I modify it. So because this model is validated. So these validations or correlations is very important. So you have to ensure you have your model behaves dynamically the same with the actuals. Then you can perform what we call this structural dynamic modifications or SDMs on that particular machines. Okay, virtually means in your CAD models. Okay, so you can do a lot of trial and errors, many different modifications if you want, as you want on that particular virtuals without touching the actual system, actual machines, right? So once you have satisfied with your machines modifications in virtuals domains, mean in your computational CAD models, and you see it's good, your shift in natural physics is good, the stress analysis, through stress analysis, you found that the stress is also good, not exceeding the strength of the material itself, then you accept that the modification, then only you fabricate that particular modification and apply it or install it into the actual systems, right? So then you can test it, okay, experimentally, okay, you can perform again the operating deflection shape analysis or as well as the model analysis to ensure, yeah, the shape of natural frequency is good in actuals after the modification, and the vibrations through these operating deflection shapes are all within the low vibration. Low vibrations limit. So everything is good, then you can store it and you can store all these models, right? And as well as analysis data in database in the futures. If you want to further enhance it, then you can take it and further enhance it, right? So that is basically what we call DDVs. So if we look into individuals, so first ODS is to determine deflections of the structures during operations. It gives us the actual vibration values, right? We measure using sensor, we get the actual vibration values as well as its shapes, okay? The deflection shapes, okay? How it moves. Right, let me show you. Right, so from here, right, ODS, you can see that from ODS itself, from a very complex so-called this machine itself, then through this ODS analysis, right? So it's a techniques that determining the amplitude and relative phase at various location of machine, and hence the motion of the machine can be determined while it is operations. So the whole idea of ODS is to, you see, this thing is running at probably 70 hertz, right? It's very high frequency where our eye definitely cannot see it. The vibration amplitude is probably in microns, micrometers, which is where so small at our eyes, we definitely cannot see it also. Through this ODS with the sensor itself, right? So mapping to the entire this particular model itself, then through some signal processing, we can amplify the amplitudes as well as its motions. So you can probably see that how these particular machines move, okay, during its operation at 70 hertz at a very small micrometers scales of vibrations, right? And you can see that in this particular case, top views of this particular machine, you can see that these particular machines, the coupling here between the pump and also the gearbox itself is having a high vibrations in this case, right? So that gives us some sense of how this particular machine is vibrating, okay? The directions, the shapes, and where is the highest vibrations. Okay, so you know that it is here. And how high is it? You can also know it because you are measuring its absolute amplitude, vibration amplitude of each particular motion, each particular point. You are covering the entire machines. Right, then another experimental technique that we are using is experimental mode analysis. So experimental analysis is used to determine the natural frequency, resonance point, the mode of vibration, the mode shift, as well as the dampings. Right. So it's a measurement technique of determining the dynamic characteristics of given structures, namely natural frequency, mode shift, and modal dampings. So that you remember, experimental analysis is to determine the system dynamic characteristics, your transfer functions. Here we are saying that it's a frequency response function. So that frequency response function tells us where is the natural frequency, what is the damping. If you can see that this particular peak is sharper, so, okay, lower damping. This particular peak is wider, higher damping. So that give us all these informations, right? So from here, we know that these vertical pumps, you having a natural frequency of 46.4 hertz, okay, the damping of 1.3%, and how it moves, that is how it moves, how it vibrates. Okay, so if I know these informations, right, I know that if my pumps, okay, it's motor, I'm running at 46 hertz, so I will see excessive movements as contributed by these particular modes. Okay, dominance by this particular mode, where this particular pedestal part will have a higher vibrations, motions. Okay, a first bending modes, as you can see here. So that gives us how to explain. Okay, with this information, we can explain, we can know the dynamics behind why it vibrates like this, right? So from model analysis and ODS, we can identify the modes that contribute to the deflections to this, because all the motions of these actual motions of during operations, during operations are all contributed by the modes. Depends how dominant is that particular modes contributing to this. So knowing this, we know how dominant that part, a certain mode is contributing to the overall vibrations. Right, then we have finite element coming in, okay, computational mechanics. Okay, in this case, finite element analysis is used to first we model the structures, do CAD modeling, then we perform computational model analysis, compare it with experimental model analysis. Experimental model analysis tells us the dynamic behavior of the machines. Computational analysis telling us the dynamic behavior of the CAD models. If both of them telling me the same results, the same dynamic characteristics, meaning my CAD models behave the same with the actual models or actual systems. Okay, based on the results of the measurement and computation mechanics, problem can be acceptance. So you will know your high vibrations in this case is due to structural dynamic weakness, or what we call the low resistance issues or dynamic design issues. Here sometimes we call structural dynamic weakness issues. The structures or the machine is dynamically weaker because of the dynamic design issues in this case. All right. Or it's an external excitation problem. So if you cannot see any natural frequency coincide with excitation frequency, and you still observe very high vibrations, and from there you can see, particularly at your driver side, very high vibrations, then probably that at one time higher in your spectrums, then probably you can relate it to this is external excitation problem, which is causing unbalance, caused by unbalance. So from here, you will know it's a force issues or it's a low resistance issues. All right. So if you are looking into finite elements, okay, it's a process of determining the dynamic characteristics, okay, finite element analysis of the structures. So you're performing computationally the model analysis in the computation domains. So here you will get the models, natural frequency as well as mode shapes, and you know at these particular frequencies how it vibrates. So if this particular frequency and the mode shapes are same with the what you have obtained in EMA, then you are saying that this particular model that you built is validated is behave the same with the actual systems. So in this case, I mean, these finite elements, because the way it is being modeled, being solved using this multi-degree of freedom discrete, what we call discrete modelings, or what we call finite modelings, then damping is basically it is solved under undamped undamped. It treat this particular model as undamped, so that it's solved to get the natural frequency and mode shapes. So no damping is being solved, being determined under computational model analysis. Right. So once we have getting everything's done, right? We know, let's say we know that it is the problem is not force related, is a low stiffness, a resonance related, or structural dynamic weakness related. Then we can perform virtual modifications, right? So virtual modification is a structural dynamic modifications where you modify on your CAD models, not modify on your actuals. So until you satisfied with your modifications, then only you fabricate on that is the modification that you satisfied, okay, through some mechanical drawing. You go and fabricate and modify on that particular actual machines, right? So of course, once you have modified, you have to test it, right? Test it, and everything is good, the data is good, then you store in database. If no good, then you can go back to your modification again. Right? So if you have a very good models, whatever that you obtain here, whatever that you obtain here should be reflecting into the actuals. So based on the communication with your clients or with your superior in terms of the modification, sometimes the modification that you propose may not suitable or may not applicable in the actual conditions. Then probably you have to make a feasible, applicable modifications in the virtual domains, okay, or CAD model, your CAD itself. Then once you satisfy with your virtual modifications, then you can actually apply it or fabricate and install it and test it. All right, so that is the entire DDVs. All right. So in picture form, so basically that is what's the flow charts, DDV flow charts. You have actual structure, which is cooling tower, cooling fans. Then you perform experiment techniques. You have wire mesh models where you give you the natural the mode shapes as well as the operating deflection shapes through ODS and EMA. Okay, so at the same time, you can build a CAD models in here. It performs FE modeling and perform FE model analysis to get the same dynamic behavior, dynamic characteristics with the actual EMA. So one is good, correlated, then we say that this model is validated. Then you can perform problem identification. Then you can perform structural dynamic modification. Okay, so you can, knowing the problems probably is a weak dynamic weakness, and you have a very very flexible bending motions at this motor support. So if you can perform a modification on strengthening this motor support itself, then probably you can shift the natural frequency away from its excitation frequencies, rectifying the resonance or structural dynamic weakness issues. Then you solve it. Then in fact, if you satisfied with the modifications, okay, then you can fabricate and test it, right? So that is what we call DDVs. All right, so that is the DDVs. Okay, so later on next week we have these laboratory sessions. So we will be learning how to perform model analysis or experimental model analysis at labs, as well as operating deflection shape analysis. Only these two, right? looking in these two analyses, so probably you have to analyze, okay, what is the problems, what is you have to explain or discuss your results based on the ODS results. So the ODS result, you will give you the spectrums, overall spectrums of all the measurement points and the motions, the deflection shapes during operations. So you have to explain the deflection shapes, okay, why it vibrate like this at this high peaks, high vibration at behaving like this through combining it with your model analysis results. So combining experimental model analysis and ODS analysis, you explains, okay, the factors that affect things, this so-called vibrations of that particular lab test strips. Right, so that will be your task in next week laboratory sessions. So if you can look into this, some introductions or model analysis. So just recap a little bit, so that we have more time focusing on our laboratory sessions next week. So I have later on share with you this. You can go through this also. So model analysis, as I mentioned to you, is a techniques to determine this inherent dynamic characteristics. So these dynamic characteristics are basically it comes inherently means it comes since day one. When this particular thing once assembles, right, you have a new set of natural frequencies or these dynamic characteristics. It since day one or since it born, you have these dynamic characteristics. So we are actually determining or extracting this set of dynamic characteristics. Right. So there is one technique that you will be using. So what you are doing here is in model analysis. So if you still remember our in system outputs, right? Input output relationship, right? So to get our systems informations or transfer function, we need to have in and out. Out over in, we'll get the transfer functions, right? So what we need to do is we give an input, okay, an impulse. Then we measure the response due to this impulse, right? And this response due to this impulse divided by the input itself, then it gives us the set of the information of the system, or what we call the transfer function. All right. So that is what it means. So if I give an impulse to a systems or this particular beam itself, the response that I obtain is a superposition of a number of modes of each mode vibrate at its own natural frequencies. So I will have, if I'm not at, I give an impulse at this particular point, okay, at this particular point, I will have a response of this, respond with this contribution, plus this, plus this, plus this. Mode 1, mode 2, mode 3, mode 4. That is corresponding to this, right? And combining these four natural frequency will give a very complex superimposed sinusoidal, decaying sinusoidals, right? Impulse is a transient signal, so that if this particular signal itself consists of its natural frequencies, or we call the dynamic characteristics information, consists of first four modes. Okay, so if you give an impulse and the meters here, right? Like I mentioned, if you're given an impulse and meters here, right, you will excite this mode. So you have this, you excite this mode, you have this, but you do not have this and this. Mode 2 and mode 4 you don't have. So your response due to the impulse will be only this plus this. Okay, so that is what we have learned just now. Right? If this transform to frequency domains, right? If you have this transform to frequency domains, the time domain transform to frequency domain, then you will have this peak, 4 peaks, four sinusoidal at different frequency give you 4 peaks. Each peak give you a natural frequency 1, 2, 3, 4, right? So the values of sigma 1, sigma 2, sigma 3, sigma 4 are different, which is the dampings, and it decides the width or the broads of this particular peak. Sigma is higher, then you have a broader peaks. Sigma is lower, you have a sharper peaks. Right. So the whole idea of experimental analysis is to extract this out. Right. Experimental method used in investigating vibration characteristics. Of course, it required the system to be shut down. Okay, you have to you see because you want to extract this so-called system informations, you have to give a known inputs. You have to measure the output or the response due to these known inputs. If it's running, so when this particular machine is running, you give an input. So the response or the vibrations response that you measured will be due to this input plus the runnings, okay, running conditions in noise or whatever response coming from the running conditions, right? So that's why it have to be shut down. No unaccounted excitation force induced into the systems, okay, only purely input plus the response due to input. So dividing this out over in, you will get this. So that is the whole idea. Right, so the methodologies I will cover during on site. I mean during laboratory sessions easily. I mean it become easier. So these are 4 main methodologies. So we will cover one by one next week on this. ODS, like I mentioned, is a technique to determine response of the whole structures during operations. The study to determine the response of the whole structure during operation is termed as ODS, Operating Deflection Shape Analysis. This is another one that we want to perform. Okay, so to perform ODS, the system have to be in operation, have to be running. If it shut down, you cannot perform ODS because we want to get the response as well as its motions during operations. So why we want to perform ODS? Because we want to know how it vibrates, how it moves during operation. And because the actual motion is too fast, the amplitude is too small to be visualized by our naked eyes. So the whole idea of ODS is to slow down the motions, amplify the amplitudes, so that using some DSP techniques, so that we can visualize the motions, how it moves during operations, and we know the severity or intensity of the vibration. There are 2 techniques. ODS, we have a frequency domain ODS and time domain ODS. Right, so in our labs, we will only perform a frequency domain ODS. So later on, I will tell you why time domain ODS is not that recommended in our case. Right, so this is frequency domain ODS. Right, so the whole idea of frequency domain ODS, you only it is very similar to what we call our model analysis. Our model analysis, we are giving an input, we are measuring the response due to the inputs. The ODS itself is just measuring the outputs, okay, the outputs. Okay, but then you still remember we need the motions, we need the shapes, we need the phase, right? So we need another reference sensors, okay, that to give us the relative phase. Remember the relative phase that we are having? We learned before the phase, right? That gives us the directions of each measurement points with reference to the reference measurements, right? So that is the whole idea. So can be obtained in a similar way in model analysis. So you need 2 accelerometers, one fixed, one is moving. The fixed one is the reference one, where your moving accelerometers is to get the amplitude of the vibration, as well as getting the phase, relative phase related with reference to these fixed accelerometers. Okay, so the amplitude is getting by auto power spectrums. I mean to get magnitudes. The phase is through cross power spectrums. Right, so that is additional information. So there is only 2 sensors needed, okay, and through some signal processing techniques, then you can get the motions of this particular any particular systems that you are measuring. Whereas in time domains ODS, right, it required you see it required many sensors. And it have to be recorded. Your vibrations have to be recorded simultaneously. So in frequency domain ODS, whatever the sensor, it usually under steady state operating. So if you are at the fixed frequencies, running frequencies, then usually you can use what we call a frequency domain ODS. Okay, so you get the time signals. Okay, through auto power spectrums, you get into spectrums, right? To get the magnitudes. Cross power spectrum, you get the relative phase. Whereas time domain ODS, you need n sets of sensors. Depends on number of nodes that you want. If, for example, this particular plate itself, I need to know the motions of this part or the entire plate itself. So then I need 1, 2, 3, 4, 1, 2, 3, 4, 20 sensors. If you need a 20 sensor, right, and you need 20 channels in this case. So basically, the cost itself is higher in this case. So at lab, we don't do that. Even at site, usually we also don't do that because it's too expensive. In this case, you need sensors, number of sensors, and also number of acquisitions channels, right? So we do recommend frequency domain ODS, but time domain ODS is particularly useful when your frequency is non-steady states, non-steady frequency is running is non-steady or randoms, then transients. Transient type of excitation, transient type of condition, non-steady, then time domain ODS is useful because it is recorded simultaneously or synchronously. So you put in all your sensors, then and it's faster. In this case, you set up everything, then you capture all these sensors data at one time at similar times, synchronously or simultaneously. So that give us, if you have 4 sensors, 4 time waveforms, right? So you have how it moves at different times. Even its opposite direction, it have been taken care of. So if you play this simultaneously, I mean sensor 1, sensor 2, sensor 3, sensor 4 at 4 locations, let's say 1, 2, 3, 4 simultaneously, then you know how it moves. When this thing moving up, then probably this thing moving down, right? Opposite directions. So this thing moving up, this thing moving down. So you know it's simultaneous. If you can play it, record it simultaneously, you play it back simultaneously mapping to the correct locations, then you can see how it moves, okay? The motion movements, okay? During operations, right? But the cost will escalate, depends on number of freedom that you want to get. If you want to get a very, the entire rotating machines, talking about usually frequency domain will take 100 points. Then in this particular case, you need to get hundreds sensor and 100 channels. So that is not possible at all. All right. So that is time domain ODS. So the methodology will be the same. I mean, later on also I will explain to you what or how to perform, particularly the frequency domain ODS. Right. Then computation modality is like what I have mentioned to you earlier, right? So I think if you go through how computational model analysis performs, basically it's a finite element analysis, based on finite element methods. So if you know or we've gone through this finite elements analysis course, so probably you will know how it will be basically solved. Okay. Basically, it's similar like a multiple degree of freedom. Basically, that is discretize your models, your CAD model into elements. So each element you have nodes. Each node basically is like your mass. Okay, your mass. Each node basically is your multiple degree of freedom mass, right? So if you can basically model in terms of n degree of freedoms, then you solve it. That particular equations, then you get your natural frequency damping and motions. Right, so not going to talk much on this, but then here you need to know why we use computational model analysis, right? So the whole idea of this computational mechanics, or in this the roles of this computational mechanics in DDV is to create a virtual models or CAD model or virtual models, which is being validated and behave the same with your actual systems, right? Then allow us to perform structural dynamic modifications if needed in the virtual domains without needed to modifying the actual models, actual systems. So once the modification in actual virtual domains is satisfied, then only we translate the modification to the actuals. Okay, so that is the whole idea of computation mechanics, where you must take notes or